Hi, everybody. Welcome to another DevHeads technical meetup. And this meetup, we're going to be going through device trees for Linux and Zephyr, embedded Linux and Zephyr with Ming and Zacck. We want to welcome all of you guys and are excited for this AMA session. So this is an Ask Me Anything session. It's a little bit of a different format if you haven't been involved in an AMA before. Basically, it's just questions from the community. So everything that you guys have ever wondered or tried to figure out about device trees, either in the Zephyr context or in the embedded Linux context, we're going to be taking those and answering them to the best of our ability. Now, we do want to let you know we have put some of these feelers out into the community beforehand, so around Reddit and LinkedIn and Facebook groups. So we have a bunch of them already in the hopper. There are probably about 8 of them, and I'll be loading them up into the platform during the course of the event. But we do want you to continue adding your questions, and we'll get through as many of them as we can in the time that we have. So we're going to go for until the bottom of the hour. So keep pushing those through, and they will do their best to respond to them. I know the last time we did this was really successful. Ming was able to do some screen shares and show some live examples. We can't promise that we'll be able to solve everything because we don't necessarily know what's coming in, but we will give it a whack. And then if there's something that we aren't able to get to, we can give that a whirl after in the community. And I do want to point out that joining the community is probably pretty important here for you. So you can join us at DevHeads on Discord, which is at https://discord.gg/devheads. And I'll drop that into the respective chat channel. Now, I want to give Ming and Zacck an opportunity to introduce themselves a little bit and why we chose them to speak on this topic today. And meanwhile, I'll get some of the other stuff queued up. So, Ming, do you want to go first and introduce yourself?
So, hi, I'm Ming. I've been working in the Linux space for it's well over 30 years now, and in the embedded Linux space for over 15 years. And in the embedded Linux space, this is where we do have to play around with device trees. And I probably spend a large proportion of my time, especially on board bring up and fiddling around with things, trying to get the device tree working, as it is fun.
There's another word that starts with that.
There's another word that begins with that, but I'm too polite to use it.
Right. Zacck, how about you? Do you want to go ahead and introduce yourself?
Yeah. Hey everyone, I'm Zacck. I'm a software developer, and I've been making software for almost 15 years now. And I've mostly been working on very low power equipment, basically mobile phones and embedded computers. And I'm happy to be here. On Zephyr and device trees in Zephyr, this is whenever you do something outside of the example code that Zephyr gives you, which is a lot, usually you have to cobble up some hardware together. You usually have to deal with device trees, and then suddenly your 3-week project becomes a 3-month project. So we're here to find out how to deal with and how to navigate device trees today, for sure. I look forward to this.
Cool. Zacck, can you give us a little bit of a flavor of your experience with Zephyr in particular? I know that you're sort of an early entrant into it, and you've been messing around with it for a while here. So if you want to tell us a little bit about your experience?
Oh, yeah. So I would say basically a year into, maybe less than a year into using Zephyr. But I'm familiar with the real-time concepts of it. The bigger part I'm learning in Zephyr at the moment is how to use the Zephyr ecosystem to my advantage. So this is how to find code. You need to know where to find the code, and you need to know what to go and read so that you can fix what you're going through right now. And you need to be able to interpret what you read so that you can fix it. And I would say this is kind of what I'm going through at the moment. And it's quite, it's nice because I understand software enough that I can do stuff in Zephyr. But even with that prior information, I still need to understand how Zephyr itself works. And I think the past few months have been us showing someone picking up Zephyr in anger, or rather for production, in the open, basically. And yeah, I'd say that I think I'm working on my second project in Zephyr right now, which is the motor control thing that we are going to demo soon. But yeah, so a few months in, quite familiar, hoping to get more familiar, if that answers the question.
Great. And we'll let you. Yep, thank you. And we'll let you guys know a little bit more about this motor control project that we're doing in the DevEz community with Zephyr a little later on during the presentation. But Ming had a little bit of a background that he thought would be good to make sure that we all level set. So we put together a few slides just to make sure that we are all contextualized. And here's slide number 1. Do you want to walk through it, Ming, and then I'll just say push the slide and I'll push it for you when you're done?
Yeah, I'll give you the next slide thingy. So it basically, I'm just thinking that a lot of people talk about device trees. A lot of people will curse device trees because when you first come into them and they're going, this is actually quite a complicated setup. Why are we doing it like this? So just a little bit on the history of how we got here and why we got here. So device trees, although they're in both the Linux and in Zephyr, they started out more in the Linux world. And it is coming from when we're bringing up a board under an embedded Linux system, we have to have a board file to tell the system how to actually initialize all of the hardware that's attached. So there will be, for every board that you've got, there will be a file that says, this is what is attached, here is all of the code, so here are all the functions. So all the functions you're seeing here are the functions that are going to be called as part of the board bring up. So this machine start, and then you've got all these functions it's going to call of the initializing the IRQs and all of the handling and setting things up. You're going to need all of this for the board. So if you have a look at the next slide, Brandon.
Yep. You seen it?
Not yet.
Oh, it's moved on my side. Hold on. Let me kill the screen share. There we go.
There we go. So this is an example of where the problem is. So this is based on, it was an early 3 dot something of the kernel. I can't remember where I pulled this configuration from. So we've got 2 different boards from 2 different ARM type development boards. And they therefore have to have 2 different bring up files. And we've got, if you're looking at the actual configuration of these, they are almost identical. But what we'll therefore have to do is now need to maintain 2 separate files for something that has just got a small variation in the hardware configuration. So you're adding in a whole bunch of just general maintenance issues. And it's mainly in the ARM world that this was coming about, because the problem with ARM is that it's so popular. And there are so many little development boards that are being developed using ARM chips. And every single one of them needed to have a bring-up file board, which therefore needed to be maintained. If you move to the next slide, and we will see the response to the problem. Now, Linus Torvalds is known for his tact and diplomacy and calm language. What he basically did is he went, this is a mess. If you don't, please, make an effort, then he won't pull. He will actually cut out all of the ARM code. So the ARM developers went, okay, let's go and do something about this. So if we move on to the next slide, what they did is they started hunting around for what is a solution that we can be putting into this. And they came across the open firmware. Now, it hasn't moved to the next slide, Brandon.
Yeah, it's lagging.
There we go. So There was an open firmware project that preceded all of this of an issue. It was a bunch of guys that had got together and said it would be really nice to be able to have a meta description of what hardware we've got of things. So what we'll be doing, or what the whole open firmware does, is it splits out the description of the hardware from the implementation of the hardware. So now we can just have more generic things within our kernel code, and then we can just slot in the details, as it were, of the actual hardware that you've got on the board in front of you. So not only does this now mean that you've got less maintenance because you're not having to maintain loads of different board files, it actually reduces the time to bring up boards. Because when you've got a new board, quite often they're just a variation on a pre-existing board. So now all you're having to do is potentially just tweak the device tree a little bit, tweak some of the drivers, and go. So you're now improving a whole side of that time to get things to market, and it just makes things a lot easier. So we have a look at the next slide. So what it has now done is we've now got generic bring up files. So we've now got a generic OMAP3 device tree bring up. So we've got all of the standard things because the OMAP reserve, the mapping IO, the early initialization, etc. All of those are common across all of the boards. And then we just have this DT compat, which is going to be our device tree compatibility. And that now just brings in the things that we actually need. So it's just going to be making things so much easier for all of the actual bring up and control of the board itself. And we've got another slide, haven't we? So just looking at the actual structure of the device tree. A lot of the actual device tree implementation of it, it looks a little bit like JSON. It's all about key value type things. Now, it being a tree, it starts with the root of the tree, and then you've got various nodes, and within those nodes, you've got properties, and you can also have children within those nodes, and you can come out to your tree. So you would have typically a node name, compatible, and all that is doing, this compatible bit, is just so that device drivers can say, right, I'm a device driver. Generically, I can pick up anything that is compatible with demo manufacturer, demo model, whatever it is. It again allows for generic reusability, which is the whole point of the device tree. And then you've got various keys under their values. So you can have a string, you can have a list of things, you can have data, you can have integers, whatever you're wanting. And then within your particular node, you can then have children, they can have properties and subnodes, and it goes on and on and on. If we look at the next slide, which is a more realistic example. So this is an example that I was using for a board that I had, whereby we had a cell modem that was, the power was attached to a GPIO pin. And I was wanting to be able to have a device driver that would be able to, I could send a signal to the device driver and to toggle the power to the modem in a particular way to reset from a hardware perspective. So what I'm needing to do for that within my device driver is I need to provide the information in the device tree to my device driver. So I've got a cell modem node. It's compatible with the reset modem, so that's what I'm going to be looking at for my device driver. And it's all about setting up what are the GPIO pin controls. So I'm just looking at the pin control names. I'm wanting the default. What are the values? And I'm going to be taking the values from the cell modem power. The ampersand means that that's going to bring in the values of something else that has been defined elsewhere within the tree. Key thing was also the status. The status can either be disabled or okay. And this is, again, how within a device tree, you can easily turn things on and off if they even exist on the board or not. You can have one device tree or one, 4 different boards. That one's got a modem, that one's got something else, that one, and you just put your device tree, you say, that's okay, that's disabled, that's disabled. So it's simplifying how things are going. And then I'm just saying my GPIOs I'm looking at GPIO 113, as that is where the actual power line is. And then coming down to the cell modem power, so this is defining the actual pin mux of my chip to say that I'm wanting to set this particular pin into mux mode 7, which is general GPIO. Pin muxing and things well out of the scope, but it's just how we commonly will use things in the device tree of how we can define what pin goes where. So that would be how I would be using it in the real world. Then the next slide is looking more at, especially for things like the Raspberry Pi, the BeagleBone. These are common things that we're going to be using to do our initial development on. And you'll see quite often it talks about having device tree overlays, where in your configuration file, you'll be saying that I want to add in this functionality. So it's basically allowing you to modify the device tree at boot time. You can't do it at runtime, it has to be at boot time, but it means that just by at your boot, you can now enable or disable functionality within your board by using a device tree overlay. And what the device tree overlay does is it basically is just going to take your initial device tree and then overlay the information on this. So here's an example of when I'm doing some teaching and I'm teaching Linux device drivers and I'm teaching the device tree. We set up, we do what everyone does firstly, is you have an LED that you can toggle and we write a device driver for that. But then what we'll do is we will shift the definition of the GPIO into the device tree. And then with a device tree overlay, we can start moving that LED GPIO around the place. And we can therefore change it at boot time without having to recompile the kernel, without having to recompile the entire device tree. We can just have a selection of device tree overlays and bring in the one that we are wanting at the time. So that's kind of why device trees are useful. And hopefully it just gives a little bit of background about the, yes, it is a black art. Yes, we do spend a lot of time tweaking it, trying to debug it, etc. But there is a reason behind what we're doing.
Very good. Thanks for the context. It's always good to set the stage. Appreciate that, Ming. So now we're going to get into the actual AMA portion of the event, and I'm going to take us back up to the title slide because it says it all. And the first question that we've got is, hold on, I'm trying to multitask here. Here we go. The first question we have here, and sorry guys if you're looking at this in the Q&A tab because it's going to be inverted now as they come in. First question's at the bottom. How can I see the contents of the device tree that's being used in my system? So I guess I'll get to you first, Ming.
Yeah, from a Linux perspective. So if we're assuming that you've booted your system and you're going, so what's the actual device tree look like? What have I actually got? Let me do a screen share because I can then.
Yeah, I'll buzz off. And for those of you in the tool, I'm going to be putting the current question in the chat, so you'll be able to follow along with where we're at.
So here I've got one of my Raspberry Pis that I'm using. It's actually the Raspberry Pi that I'm using to control my 3D printer. But if I'm wanting to know, what does my device tree look like? Well, under Linux, we have the proc file system. And under the proc file system, which is a pseudo file system whereby the kernel exposes its internal values through a file system, we have a directory of proc device tree. And in there, we've got all of our device tree. So if you're wanting to say, and so, what are, my LEDs? So I can now, these are GPIO LEDs. So this is how I can have a look round at what is going on in the device tree on a running system. So whatever you're wanting to do, you can now just explore the entire device tree in a directory structure, with all of the branches being directories and all of the leaves being files that you can then just count and read.
Great. Zacck, from your perspective, same question. How can you see the contents of a device tree that's being used by the system in Zephyr?
So let me pull up a link and share it in the chat, and then I'll quickly explain. So the difference between, I would say, Linux and Zephyr would be the size of the target device. Or when I'm saying size, I'm talking about how much you have in terms of memory and in terms of how much space you have on the device. So basically, what we end up having is we do not end up having the device tree source or code in the device that is going to actually run it. What we have is almost a small executable that you can carry around, because we don't have that much flash or RAM to carry around the whole device tree and be able to navigate into it. So as for Zephyr, if you want to see the device tree or for the application that you're using, number one, it's either custom device tree complete that you're building up for something really bespoke that you're building, and in which case you will know where it is because you'll have written it. But the other option, the more common option, is you're going to be using mostly, like you're going to be using the SoC or the system on chip or the system in package, or whatever, SIP, or the module you're using is going to be defined by Zephyr. And where you find this information is this link I've shared in the chat here, which basically is a source for all the device tree. First of all, the sources, which describe the hardware, and then the bindings, which really tell you. So the sources say what, and then the bindings tell you how to use the hardware that they've just described. And in Zephyr, it's almost like the embedded HAL layer in Rust, where Zephyr has provided rules for writing device drivers so that anyone can write device drivers and make them available to everyone. The same as Rust provides traits or interfaces that you have to adhere to write drivers, and then anyone can write a driver and provide it to everyone. So it's hosted in the source, but you're not really carrying it around in your application.
Yeah, Zacck, could you do a screen share real quick and just walk people through that link and show them what you're talking about? And then Ming, by the way, sorry, I kicked your screen share out so that it wasn't confusing while Zacck was talking about Zephyr.
Yep.
Okay. Just a moment. Let me move you guys to. Oh my God. Yeah, let me move you to that screen, and then I will share this screen to make sure it doesn't do a double thing. Screen built-in display share. Okay, so I'm assuming you can see my screen right now, and we are probably in some sort of bind.
Yep.
Let's go all the way out before we. So in the Zephyr code base, which is the. Can I control plus? Zoom in. This is a Zephyr code base. In here, you will find a device tree sources folder, and this is where both your device trees, the sources and the bindings are. Your bindings are going to be in the architecture. So I mostly use SD. I'm very familiar with the SDF4. So let's find the device tree for SDF4. So I'm going to go in and I'll find ST, the manufacturer, and then in here I'll find the F4 board, and I happen to know that I use F4 XG. So that's this little guy. I use this guy for S4SG, and this will probably, yeah. So this one includes the 4.7, which in turn, so I'll go quickly so that we can see the 4.7, which pulls from the 4.5, which will end up at the one at the top, the 4.5, which pulls from the 4.1, which is basically this. You end up here. This is a description of the whole system on chip. It describes how many NPOs you have. It describes the system on chip, which is the flash, which is the reset and control block, the EXTI, the pin control stuff, and GPIOs and UARTs and USARTs. This describes your hardware. And then you, on a little bit of a different layer, if you go back and then you go to bindings. So wait. I'll go back there and we'll look at something. So let's look at something we can find later. We have a USART one, okay, and this is compatible with STM32 USART. Cool. So if we go back to DTS, and then we go back to bindings, and then we come to, I think I would say there should be a UART one. All the UART ones should be together if I'm not, or USART ones, or serial ones. Serial, okay, and then in serial we should be able to find the node I was looking at on the other side, which was STM32 UART. So this YAML will basically describe what properties the other node that we were looking at in the DTS that has. So this is whenever you want to know what your device tree has with Zephyr, you're going to either dig into your code that you have locally, or you'll go to GitHub and look through whichever device and architecture that you're looking through, that you're actually carrying along, because your application will not carry, you won't be able, like the way Ming did it, he went into his actual application computer and looked at his device tree. You won't be able to do that with your code, because in real time, you have very minimal devices and you can't carry all of this around, basically. If that answers where to find that information. Yeah, I think.
I was just going to make a quick comment on seeing how you are navigating through the device tree sources there, Zacck, highlights one of the delights of working with device trees.
Yes.
Where you're saying you started with your initial DTS,
yes,
but you then had an include DTSI. So these are include files. So you're then having to open up that file and browse through that one. Where there's an include, there were 3 includes in that one. So you have to open up those. And then you now have to flick between all your tabs to try and find what is the actual value that you're interested in. And that's why working with device trees can be a nightmare.
It is a nightmare, but you have to consider the other side of this. The other side of this, I would be reading header files and actual functions that describe the drivers. I would actually have to go and read the driver. In all of this that I've done right now, we just looked at the description of the hardware, and then we came back and we looked at the binding, that says, how do you use this hardware? But the alternative to that is to actually go through the code itself and try and determine what is happening. And whenever your one pin changes, you have to go everywhere the pin is mentioned and do stuff with it. So it's difficult, but it's the easier sort of difficult rather than the other.
It's one of the things I always talk about. Yeah, device trees aren't easy, but they're a lot easier than the alternative.
Yes. Yeah, that's true.
And I swear this isn't scripted, but the second question was, how do I read the contents of the device tree in my device driver? So, anything else to add, either of you, on that?
Well, I mean, there is, to actually read it in your device driver, I've got a little bit of sample code. If I come back to sharing my screen again for a moment. So here's a tiny snippet of an extract from a device driver. We're going back to the thing where I had that demo LED node within my device tree. So within the Linux kernel, we've got various ways. We can either be looking at trying to write a complete platform driver, which is what I did when I was looking at the modem reset line. I wrote a little platform driver that was able to pick up the compatibility and put in a whole bunch of logic. But if I'm just wanting to extract a value, then there is a OF. Now, a lot of the device tree calls within the kernel will be an OF prefix coming back to, it comes out of the open firmware. So that's why they're all OF calls. And there is an OF find node by path. And what that is going to do is search in the device tree until it finds the particular node that I'm looking for. Then that sets that to be my root node to start doing things. And then what I'm looking for is I want to know what the value of the GPIO is so that I can bring that into my device driver. So I've got an OF property read, and you've got an OF property read string, a read boolean, read uint, U16, U32, U64. So that's how we can now read all of the data into our device driver. And within my GPIO number, I can now do something with that in my device driver. So there's a bunch of function calls within the kernel that I can just be calling to extract the actual information that I'm interested in. But I need to know that it exists in the first place.
Zacck.
The Zephyr, if you could just keep Ming's screen for a moment. So the Zephyr one is going to be largely the same. However, we're going to be dealing with macros that are prefixed with DT rather than OF. And I think in Linux, it gives you a header and you have functions you can pull from that header. And then in Zephyr, we basically have a header that provides you with macros. And they're suspiciously
Ming, can you pull your screen? Ming, can you pull your screen again? Actually, this might be a pretty helpful way of describing is having Zacck describe your example.
Yeah, it's fine. So that's actually perfect. So instead of including a Linux of.h, you'll include device.h. And this would in turn include something called device tree.h. This is your actual device tree that is generated from the bindings and the device process and your device drivers. This is another body of code we're not even looking at. And then you would end up having, I'm pretty sure, I might be mistaken, I could eat my words, but we do have in Zephyr DT find node by path. The same function is just prefixed by DT. And GPIO now DT property read of unsigned 16-bit. It's suspiciously similar, but it's not the same. Once you understand one, you can understand the other, but then there's nuances in dealing with both, and you will have to go into documentation. You can't just carry over information, but you can carry over know-how, and then you'd have to fix it with the new information, whether you're going from Zephyr to Linux or Linux to Zephyr. So we have the same system, but it's just DT-based rather than OF-based, I would say.
One thing I did notice when I was flicking through the Zephyr, because I always get curious about what's happening on the other side. Yeah. And I'll say that the Zephyr documentation on the calls were actually quite clear.
Yeah.
Which was really good compared to, I'll admit, when I started looking at the documentation calls on the Linux side of things, it was okay, so what does that do? Where did these come from? That it wasn't as clearly documented. I think Zephyr learned from the mistakes of clearer documentation.
And Zephyr is much smaller than the Linux code base, to be honest. They look similar. They're both operating systems, but one is like a mouse and the other is like an elephant. There's a lot.
This is a Zephyr specific question. I skipped over one, so we might jump around here, but just keep an eye on the chat and you'll see the current question listed here. Current question is, this is a Zephyr question. I've had a bunch of issues getting an STM32H755 to run with just the M4 core. Sysbuild doesn't work without consuming 6 sectors for a hello world. And then a UART refuses to work unless I enable the shell module, in which case it spits out garbage. I've asked how to structure the ADC driver and got no input. All of my issues could be because of my inexperience. I really like Zephyr. It's got a lot of promise, but definitely needs better documentation in the source code. Zacck, can you comment on this issue?
I need to find out whether the H7 is it a MCU or an application?
That'll be. I'm pretty sure that'll be an MCU. Let me double check too.
Well, okay, so it is a dual core MCU. So that, and now you're coming into SMP stuff, which is very young in Zephyr. And I know that's not the point of the question, but we're not. Zephyr isn't jumping into doing dual core stuff yet, because that's more the land of FreeRTOS in real time land. However, I think this question is trying to address too wide of a base, because there could be stuff here that is affected by the device tree, but then there's stuff that we don't know whether it does. Like using sysbuild, I'm not so sure why you end up using 6 sectors just for hello world. And then I don't know what we would need a description of what you're trying, so that we can kind of debug that and tell you why UART doesn't work. It's ambiguous. However, just look at try not to use the samples, because the samples are really heavily skewed towards NRF boards. So you might need to jump into specific samples and read the source code, so that you can see how to get, first of all, what is it? UART output out of ST. And note, if you're using an onboard, debugger, this little microcontroller to debug this one, on ST, if you're on a discovery board, you need to use a physical. You need to use a physical UART bridge. You can't depend on the little debugger to give you UART. You have to use a different UART bridge to get the data out. So you might want to look at that. And then your question is a bit ambiguous for me to be able to comment on why your driver isn't working or why it would struggle. I would need a bit more specifics about what you're trying and what is resulting from what you're trying before I can. It could be anything, basically, is the answer to this question. We need more specificity, to be honest.
Okay, cool. And yeah, this is definitely an opportunity to follow up in the Discord server. So again, if you're not a member of the Discord, you can check us out at HTTPS. You know what it is, discord.gg/devheads, and putting that in the chat. Randall, I saw that you were typing something. I'm not sure if you ended up putting it into the questions tab, but feel free to ask. Next question, this is question 5, which is actually question 4 because I skipped one. And I think this is probably going to be applicable to both of you guys. So device tree syntax is very simple and clear to write. The hardest part is what to write, as you need quite enough knowledge of the hardware in order to configure a node correctly according to the reference manual or data sheet. Zacck, since you went first or went last, I'll let you go, and then Ming, you want to jump in.
Cool. You're not supposed to, this is my school of thought. I don't know what Ming will say. I hope he agrees. You're not supposed to know what to write into your device tree. This information comes from either your data sheet or your reference manual. You should be picking this information from your manufacturer. And then by virtue of how they've split out the stuff, which is you have device tree sources, which are, they just describe the system. And then you have device tree bindings, which tell you how to use the system. It's very easy to know which side goes where. So if you're finding it difficult, I would try and first of all, look at an existing device tree. And they have they have less than 20 actual nodes you can add into device trees. And it's very easy to learn all of this. Then you can go look at your reference manual and know how to copy. Because if you do bare metal development, you already do a device tree. You just do it in a very rough and primitive form. So you already know this information. It's just how that's different. I would say. Yeah. Ming?
So in the Linux world, it's a little more complicated in terms of, I have to sit there, and this is what I will be doing as part of any kind of board bring up. I have to sit there with the schematics of my board. So it will be for a bespoke board. So I have to get my board designer to send me the schematics. I'll sit there with the schematics on that to work out what the pin muxes are, what the devices are, and then I have to start adding in all of those to my device tree. Because the device tree within a Linux side has a lot more nodes. As you were seeing, in terms of when I was looking at what is available under the device tree, when you're just looking at it from the directory structure, the device tree under Linux is huge. But yes, you will need to sit there with the data sheets from the manufacturer, because you're going to need to know what the actual registers are, what the pin muxes are, all of those sort of things. You're then going to be needing to sit there with the schematics. You're then going to be needing to sit there with all of the information on the different aspects of the side of things. So yeah, there's a lot of hardware knowledge that you're going to be needing from all of the data sheets, and you can't get around that. About the only thing that I'll be doing is, because a lot of things will be under my side of the world, will be the pin muxing of all of the GPIO lines. If I change that to a UART, if I change this particular line to a UART, well, that now means that I can't use that for a SPI. I need to set that one as a SPI, but if I set that one, and you've got a complete multi-mix of how you do the lines, and there's quite a lot of time that I'm spending. And occasionally you have to go back to your EE and say, well, that didn't quite work because you've set this up, and because you've used that as a UART, it's not that out, so I can't use it as the USB, and I need the USB for that. Can you rejig the line connections, please?
Well, that was actually, so Marvin just asked, in Linux, how does the kernel handle modes with multiple compatible strings if there are multiple drivers? So I don't know if you want to speak to that, Ming.
I can speak to that as well. So the way that it will do that is when you've got multiple compatibilities with multiple drivers. So say you've got, I'm going to say the modem thing. So say that there were two different modem drivers. Each of them was looking at the compatibility of modem reset. It will do it a little bit on first come, first serve. So the device driver, the first device driver called, which I'm not sure exactly how it works out which the first one is, but there is a probe function. And the probe function enables the device driver to have a look at the device and say whether or not it wants to manage it. And it can then say, yes, I'm going to manage it, and it will then return 0, in which case the kernel doesn't look for any further compatibility. It goes, right, you're responsible for that. Or the device driver can reject it, in which case the next device driver on the list will be called and says, do you want to actually manage this device? And it will just go through all of the ones that it knows about. Because as part of the device driver, you're actually saying, these are the things that I am compatible with.
Nice.
And it will do it by, I know that it will definitely do it by most specific to least specific. So, for example, let's quickly share my screen again. So here, for example, we are compatible with a TI AM335X Bone Black. We're also compatible with the TI AM3X Bone. We're also compatible with the TI AM33XX Bone. So for all of these, we're saying that we are compatible with all of these things. And it's going to be looking at what is the most specific down to the least specific. So if there were 2 device drivers, one that is, if we're for the BeagleBone Black, because I like the BeagleBone Blacks. So if I have a BeagleBone Black device driver, and I've got another device driver that is only looking at the AMM33X bone, which is more generic, then this device driver or this compatibility and device driver would win. So it's always done by most specific to least specific.
I muted myself. Sorry. It was the dog defense. Did Pocket Beagle 2 drop yet, Ming? Do you know?
I've not seen the announcement for it. I keep on seeing a lot of the. It's available in the stores under. You can click on this to buy it, but I've not actually seen it being announced for sale yet.
Oh, maybe it's not even in stock yet.
It is a real soon now.
Exactly. Cool. Actually, Zacck, there have been a couple of comments over here about Zephyr in a broader context. One of them related to the previous question you asked. But I want to start off with Vashu asked if we're going to be doing any practical stuff with Zephyr, and I just wanted to give you a chance to go over the motor control project.
Oh, yeah. So we're building, I think one of the bigger things that DevEds is doing as a group in 2025 is we're trying to finish this year having built a golf cart or a prototype of a golf cart. And we would like to do this golf cart in Zephyr and embedded Linux mostly, but there is going to be some bare metal and some Windows stuff at some point. We'll see. The Zephyr part is going to be the real-time part that controls the power system and the charging system. And we will we will do all of this in open. You will have a chance to see this from inception, all the way from planning. We'll have documentation showing all the planning, all the initial steps. And as we're doing them, you'll see the engineering, how engineering hours or Ask Me Anything or even office hour sessions where we talk about the actual development of this system that we're doing. And you'll be able to visit the code by yourself and you'll be able to see what we're working on by yourself. So hang on and try and come to DevEds events for this year and perhaps look at the DevEd GitHub to see what we're doing on that. But there's going to be very fleshed out both Linux and Zephyr projects this year, I would say.
What's well, it's a very nice plug, but what's Zephyr doing in the project?
That's what I said. Okay. Maybe I wasn't clear. So Zephyr is going to be handling the real-time control of the motor. So when you're doing motor control, you have to handle how fast the thing goes, how fast it slows down, and how much power you're sending to it, how much power you're allowing it to pull from the battery and things like that. And when you get to those controlling such physical systems, you need real-time control. And that's where the real-time part of Zephyr shines. And that's why we chose to use Zephyr this year for this.
Are we also going to use it to manage the Ethernet and the CAN stacks?
Well, I don't know if we're going to actually use it to manage the Ethernet and CAN stacks, but we are definitely going to use Zephyr to remember. An automotive network is sort of not centralized. You could say it's centralized, but it's really a compilation of several subsystems that are speaking to each other, and by virtue of their naming, they have some importance. There's no actual little center node. You can develop your automotive network so that you have a center node that controls everything. But for what we're doing this year, we're not going to have a central node. So Zephyr will be participating in the Ethernet and the CAN networks in the automotive network that we're building, but I wouldn't exactly say it will be controlling. It will be participating in a network of other devices. I see we've asked about which device we're using. We're going to be running Zephyr on 2 controllers for this system. So there's going to be an STM32F4 mini system, and then there's going to be an engine control unit, which is going to be based on the 1060 RT controller from NXP. If that answers your question, Vashu.
Ming, you were going to jump in?
Well, I was just going to say, I mean, you're saying that you want to do it on Zephyr. We could do this on Linux, as long as you don't mind starting at some point. We'll stop the motor at some point.
At some point.
For sure.
So Ming's referring to Linux less than desirable capability in real-time control, which is where you have a system that has a lot of deadlines, and all of these deadlines are dependent on each other. And
we'll just leave Linux to the pretty stuff, like displays and
HMI. Yep. Speaking of that, one element of the system is going to be an HMI that's running LVGL, which will be running on Linux and a Renesas Linux capable board. So if you're more inclined to that side of the world, there's something for you too. So one of that question earlier where we were talking about the H7, Zacck, the H755.
Yeah.
Randall pointed out that Zephyr he thinks that the question may have been related to the fact that Zephyr uses a log of configuration variables, and it may be related to configuration variables. I don't know if you can even recall what the question was at that point, but just wanted to.
Yeah, but that I don't mean to be offensive, but that's what you would think if you look at it naively, because the main way you reach into this is by modifying kconfigs, but you can't do everything from kconfig. You actually have to do some work outside kconfig, because what you're using kconfig to do is just, and kconfig is the configuration system. The configuration system in Zephyr, and also it's named the same thing in embedded Linux, but like we've seen with the device tree, it's kind of the same, but not the same. And if you're in FreeRTOS, this is your config.h file, but you actually modify the kernel, the FreeRTOS kernel. So it's both. It is some part of it, the kconfig, and Zephyr does have a lot of configuration variables, but they're all documented, and you can go pull up each one of them and see what value it is and what you should use it for and what it needs and what it doesn't need and what it depends on. The documentation for this is quite robust. So I wouldn't say the problem there was because of configuration value. It would have been some sort of implementation that wasn't matching up to the configuration, not the configuration itself, really. Yeah.
So we've got a couple of questions here, and Sanoop, thanks for your question. I'm not sure which context you're talking about this in. Either in the Zephyr or Linux context, so could you please specify? While he does that, the next question from Omar is, what are the key differences between FreeRTOS and Zephyr, and in which scenarios would you recommend one over the other, Zacck?
Oh, man. So the key difference is going to be the BSP layer. So Zephyr has a system, a way. When you do FreeRTOS, you add a kernel to your bare metal application. Okay, so you have a bare metal. You write your own drivers, and then you control your own devices, however way you deem fit. And then to this application that you've written, you add a kernel, which is basically a fancy way of saying a scheduler. That, well, it'll say this thing is supposed to run now, this thing is not supposed to run now. So FreeRTOS is basically the scheduler part, and it comes with just that. And it's really powerful. It's really small. It can do basically what Zephyr can do. What you have in Zephyr is this BSP layer that comes with already architectures defined, porting defined. It comes with such a good BSP layer that you only need to build commands to decide whether you're building the same project for ST or an XP or some hypothetical KMU board or something. So the difference is the board support that each gives. And then also, I would say Zephyr has a larger community. And because of that, you have more people you can talk to when something isn't working. So that would be the difference. But functionally, you can do what you need to do on Zephyr or FreeRTOS, whatever way you need to. It's just FreeRTOS is more bare bones. It's just you just get a scheduler, and then you can do basically whatever you want from that. There is other versions like FreeRTOS Plus or Safe Plus or such that come with more. Some of them come with the Ethernet drivers built in as such, and you could say, but all of Zephyr code come by virtue of having access to the Ethernet subsystem comes with Ethernet code. So basically, you could say that.
There is a Randall followed up with a quick clarification. Thanks. We really appreciate trying to clarify stuff. Randall, he said it was a wild guess. A new person might be using default kconfig values, which includes lots of features and uses a lot of resources. Smells like that could really be anything. So appreciate the input there. Another
kconfig is empty by default. Sorry, so that's misleading. It doesn't come pre-populated. You populate it.
I think that probably, yeah. I think what he may be referring to here is that a new user may be confused by the kconfig. But real quick here, Ming, and we're getting short on time here. Drew pointed out that there were real-time patches added to Linux on June 12th. I just want you to comment on that.
Yeah, so that within the 6.12 version of the Linux kernel, the real-time patches are no longer patches. They are now mainstream within the kernel themselves. However, the comment of it's a little bit heavyweight to be using on a little motor control, yeah. We have a lot of baggage within the Linux things for lightweight things.
So I do think it's probably worth commenting on how real time that would be in general, right? There's been some talk about real time patches in Linux being compared to real time operating systems. It's not a hard real time, right?
It's not hard real time. I would say, yeah, I'd be happy enough to have it controlling driving a golf buggy at low speed. I wouldn't want it doing the flight controls of my aircraft. That's kind of where I'd be looking at the differences.
There's good problems that would lend themselves to the Linux real-time patches. Say you have you need to do some really high frequency trading and you want to arrange your trades in such a way that you end up making profits. That this is acceptable. If something goes wrong, you lose some money. And then on the other side, on the flight controller, if something goes wrong, 200 people are falling out of the sky. So it's different.
It's also the other instance where it's useful is if you've got a pre-existing actual full system and you don't want to add in another component of an MCU or whatever, you can just make use of the existing processor that you've got, and we can now make it more real time.
Awesome. Well, I think that's about all the time we got for today. I really want to thank Ming and Zacck for lending a hand. And then there are several questions that we weren't able to make it to, but we'll make sure to follow up with those in the server. So I'll post them in the relevant channels. You can find them and figure it out for yourself pretty easily. There's an embedded Linux channel, there's an RTOS channel, and there are a bunch of other channels if you have different interests in developing IoT systems and embedded systems. So thanks again, Ming, Zacck, and everybody for contributing. We really appreciate it, and we do this because of you. So if you want to find more, like I've done a couple of times, you can go check out the DevHeads Discord server. So it's at discord.gg /DevHeads. And if you're watching this from Discord, lucky you're already there. But thanks so much for your time, and we will see you in the server. Take care, everybody.
Cheers, everyone. Thank you so much.
Bye.
Bye.